This lesson is for FST, Lesson 3-4 on Graph Symmetry. The information pictured here in this document is mostly taken out of the textbook from page 176. I did condense some of the information and I did modify a little bit of it. Keep in mind that the focus today is on even and odd symmetry. Even symmetry is a reference to things that have symmetry over the y-axis. And a good way to remember that is to think about the parabola-shaped graph, the quadratic equation of x squared. 2, the power there is an even number, and the symmetry here is over the y-axis. If you fold the graph over the y-axis, the two halves of the parabola will line up with itself. So when you're trying to determine if other graphs are even, try to imagine if they would have the same symmetry like a parabola would. For odd functions, I want students to try to picture the cubic function, x to the third power. That is an odd function because it's raised to the 3, and the 3 is an odd number. The graph of the cubic function mimics the parabola-shaped graph in quadrant 1, but the other half of the parabola is twisted down into quadrant 3. If students spin their picture right now of this cubic function and turn it upside down, they'll notice that the shape of the graph looks identical to the one that I have drawn. If you spin a graph 180 degrees and turn it upside down, but it looks the same as what it did originally, that's considered odd symmetry, which means it's symmetric about the origin. I prefer to refer to that as rotation symmetric. But the book will refer to odd symmetry as symmetry about the origin. Know that that's the same as a function being rotation symmetric. It is possible for a function to have symmetry over the x-axis, but there is no special name for that, so we would say it's neither even or odd. When students are transforming coordinates and trying to show that those coordinates are either even or odd, they will simply follow the template here that's listed in this document. When you have a coordinate and you're trying to show that it's even, you simply modify the x part of the coordinate to become its opposite. If you're trying to take a coordinate and change it to being odd, you would simply switch the sign of both the x and the y to their opposites. Our focus today in this lesson will be to transform equations using the information given below that. When you take a function and input a negative value, if it's even, the function will remain unchanged. If a function is odd and you fill in or plug in a negative value, the entire function will become its opposite. So those pieces of information are listed here in the table. I also summarized them in words down below. So we're going to do a bunch of examples. For the coordinate piece, the students will not get an example in this video. They will simply just practice those in the homework. So our first example is if you have f of x being x cubed minus 5x, you want to decide if that's even, odd, or neither. Just by looking, it seems like it's probably odd, but it is important that students take the time to prove it by plugging in a negative number. So you must plug in a negative x and see what happens. And again, we're going to be following this information here to determine if it's either even or odd. Since we're headed towards odd on this particular function, we are hoping that the whole function goes to its opposite. So I'm going to plug in a negative x, and I'm going to simplify and see what happens. If I do negative x times itself 3 times, it remains negative x cubed. When I do negative 5 times negative x, I get a positive 5x. Comparing the original blue equation to my new transformed equation after I've plugged in a negative, I can see that the x cubed went from positive to negative, and the negative 5x changed from negative to positive. So the entire function has gone to its opposite from what it was originally, so that does indeed prove that that function is odd. The next example has the function g of x equaling 4x squared. Most students can look at that and know right away that it's probably going to be even. To prove that it's even, we're going to plug in a negative x. If I plug in negative x and simplify, negative x times itself is positive x squared, times 4 is simply going to be 4x squared. So I plugged in a negative, and the original 4x squared has remained unchanged. So that does indeed prove that it's even. One more example here of h of x. We've got 1 over 2x cubed plus 3. Keep in mind here that only the x is being cubed. Upon my first look at this, I see that there is a odd power on the x, so my first gut instinct is to believe that it's probably odd. If I plug in a negative x, let's see the result. Negative x cubed, everything else remains the same. Negative x cubed is going to result in a negative x cubed without any parentheses, and that times 2 will turn into a negative 2. So on the bottom I will have negative 2x cubed. The top has remained unchanged, and the plus 3 has remained unchanged as well. So now if I compare the original to my new one, the fraction has gone to its opposite, but the 3 has not. So we did not prove that it was odd. If we had, this 3 would indeed be a negative number. Since it's not, we have proven that it is neither. So students have been given now an example of an odd, an even, and a neither. One other thing that happens in the homework is students are asked a lot of questions about asymptotes. So I want to talk to students a little bit about that with this last example. We have the function g of x being 1 over x plus 3 squared plus 7. It's important for students to recognize that the parent function, if you took away the 3 and the 7, would be 1 over x squared. And the graph of that is what we have been calling in class the volcano. The asymptotes for that graph are the x-axis and the y-axis. The vertical asymptote there would be x equals 0, and the horizontal asymptote is y equals 0. So what I would like students to do next is try to come up with the rule that would have transformed the original parent function into g of x. A reminder here that the rule and the equation are always going to be opposite of each other. Right away I can see that the x in the equation is being added to a 3. So in the rule, I know that that's going to be a minus 3 for x. The y portion is always a little bit more tricky. Right now there is nothing happening to the y, but this 7 should technically be on the other side. So I'm going to rewrite my function with a y instead. And I'm going to use a little bit of algebra here to move that 7 back over where it belongs. So that 7, if I brought it back over, I would be subtracting 7 from both sides. So this is really the equation that I'm working with. So now that I've got it in the correct format, I know that the rule is going to be opposite of that. So it's going to be y plus 7 in the rule. So now if I look at and think about graphing this, remembering that the original has those two branches in quadrants 1 and 2, and the asymptotes on the x and the y axis. Keep in mind that that original vertical asymptote would have been at x equals 0, but it is now going to be over here at 3 to the left. Remembering that the rule applies to the graph directly. So if we have an x minus 3, that's a move or a slide of 3 to the left. So that equation is x equals 3. X equals negative 3. The horizontal asymptote, which would have been originally at y equals 0, is now going to move 7 up. So if I count up, here I'm just going to estimate because I don't have room to actually draw it. If I move that horizontal asymptote up to 7, that equation will now be y equals 7. And then if I redraw my branches, my new branches are going to look like that. So they were down here before, and now they've moved 3 to the left and 7 up. So if you look at the two equations now of my asymptotes, they do somewhat match with the rule that I wrote. If you take the rule and simply put equal signs in after the letters, you have your equations for the asymptotes. So if you say x equals -3, there's your asymptote equation for the vertical one. And if you say y equals +7, that's your equation for the horizontal one.